Okay, so first let's talk about the Fibonacci sequence, which is 0, 1, 1, 2, 3, 5, 8. If you don't know about the Fibonacci sequence, it is defined by this recurrence relation, where we have the base cases f sub 0 is 0, f sub 1 is 1, and then for n is greater or equal to 2, we have f sub n is defined by f sub n minus 1 plus f sub n minus 2. So using this recurrence relation, we can compute any term in the sequence. For example, f sub 2 is by definition f sub 1 plus f sub 0, which we know are 1 and 0, so f sub 2 is 1. And similarly, f sub 3 would be f sub 2 plus f sub 1, so that's 1 plus 1 equals 2. So we can actually just turn that recurrence relation into a program itself. This is called recursion. You see that we call the function itself inside the function, which might lead you to think that it might lead to like an infinite loop, because you keep calling yourself and it's probably not going to end. But in fact, it is going to end, because if we look at our calls, we call fib of n minus 1 and fib of n minus 2 when we call fib of n. So n is always decreasing. And eventually it's going to get to the base case where n is less than or equal to 1, where it's going to terminate. And let's see an example of that. If we have the fib of 4 call, it's gonna, so since n is not less than or equal to 1, we're gonna call fib of n minus 1 first, which is fib of 3, and the same thing happens. It's fib of 3 is gonna call fib of 2, and then fib of 2 is gonna call fib of 1. And here we get to a base case. So fib of 1 is gonna return 1 immediately. So we have that, and then fib of 2 is gonna continue its addition and call fib of n minus 2. So fib of 2 minus 2 is fib of 0, which returns 0. And fib of 3 is going to continue calling fib of 3 minus 1, which is fib of 1, and we know that's 1. And then this just continues, and then that. So we eventually get fib 4 equals 3. So if we look at the entire call tree, this is every call leads to two different, usually leads to 2 different calls to the same function. So this is actually exponential. And if you call on fib of 100, it's going to take around 30,000 years to compute. So that's really bad. So how can we optimize this? If we look at these 2 subtrees that we circled out, they're exactly the same. So we've evaluated fib of 2 already, then we don't need to evaluate it again. So in fact, we can just memorize our answer for fib of 2 the next time we call on it. So this is what we call memoization. You see that we use an array to save the values when we first calculate it. So the next time we call on fib of n, if it's already calculated before, we just return that value directly. So if you look at the code, if it's n less than or equal to 1, then we return the base case. And if fib memoization of n is 0, that means we haven't calculated this before, we do the recursive call. Otherwise, we just return the calculated value from before. So this is actually O of n as opposed to an exponential solution. And if we compare the 2 call trees, you can see that the one on the right is a lot less cluttered. And another way we can calculate the Fibonacci sequence is bottom up. So we just calculate f sub 0, f sub 1, which are the base cases. Then we just keep building it. So we can then do f sub 2 is f sub 0 plus f sub 1, f sub 3 is f sub 2 plus f sub 1. And that's also O of n. And that leads to our first problem, Riječi. You can use that link to see the problem. Tony, can you check if the contest is working? All right, I'll give you a second to look at the problem and I guess think about it. All right, let's continue. So you've all read the problem, right? Give them some thought. All right, so actually, anyone want to talk about their thoughts about the problem? If not, we'll just continue with the presentation. Okay. So at the beginning, with the 0 button presses, we start with the string A by itself, right? And we have the count of A's in the string and the B's in the string also in this table. So what happens when we press the button once? The A becomes a B, right? And then we press the button again, becomes BA. Press it again, the B becomes a BA, the A becomes a B. And the corresponding numbers of A's and B's are on the right. And if we continue, we can kind of see a pattern that showed up before. If you couldn't recognize it, that's exactly the Fibonacci sequence we just talked about. And in fact, the number of A's in the string after n button presses is F sub n minus 1, and the number of B's is F sub n. So we can just write this code along with the implementation for the Fibonacci sequence from before, and we're done. But is that satisfactory? Not really. We really want to know why that is. Why does Fibonacci sequence show up here? Okay, so let's call the number of A's and B's after n button presses A sub n and B sub n, so we can do some math. Yeah. So initially, we start with the string with only an A. So A sub 0 is 1 and B sub 0 is 0. Is that clear? Okay. So what happens when we press the button? The A's in the string become B's. The B's in the string become BA's. So for every new string, if it has an A, it comes from a B from the previous string, right? Give me a thumbs up if that makes sense. Okay, thank you. And every B from the new string comes from either an A or a B from the previous string. Thumbs up. Okay, thank you. So let's see an example. This is the string after 5 button presses. It goes like B, A, B, B, A, B, A, B. And if we press it again, B's become BA's, A's become B's, and that's a new string we get. And let's see all the A's in the second string. All of them correspond to a B from the previous string. So A sub 6 is B sub 5. And if we look at all the B's in the second string, it comes from every single character from the first string. So B sub 6 is A sub 5 plus B sub 5. Is that clear? Okay. So now we have a recurrence relation, and we had an initial case before. So we can just write that into a recursive function with memoization, of course. So this is, if you look at the if statement, n equals 0, that's the base case. So A is 1 and B is 0. And otherwise, if A sub n plus B sub n is 0, that just means we haven't calculated A sub n and B sub n yet. Then we first calculate the n minus 1 case, and then we can calculate for A sub n and B sub n from the answers for n minus 1. So does this solution make sense? You have any questions about the solution? If not, then give me a thumbs up. Okay, so I'm not seeing thumbs ups from the left. So so what exactly about the solution isn't clear? Okay. Okay, that's a good point. Because we're trying to calculate two different numbers, right? So A and B. So I don't really want to like return two different things, and I'll have to use a pair or some data structure. So I just stored it in the arrays A and B. So I store the return values in A and B. So I have to solve n minus 1 first to make sure that A sub n minus 1 and B sub n minus 1 are calculated. So they're just not the default value. Yeah. Yes. Sorry, could you repeat the second part? Yeah. Yeah, exactly. So that's how recurrence relations work. You have a base case. In this case, it's n equals 0. And then you have, if you look at the bottom two lines here, this is the recurrence. So a sub n is defined by b sub n minus 1. B sub n is defined by a sub n minus 1 plus b sub n minus 1. So we want to know what a and b sub n minus 1 are first before we can calculate for a sub n and b sub n. And to calculate for a sub n minus 1 and b sub n minus 1, have to calculate for a sub n minus 2 and b sub n minus 2. So it continues until you get to the base case. And then you can plug it back in to calculate for every term afterwards. So now, is the solution clear? Thumbs up? Okay, so this part is the memoization part. The solution works without the else if it's just an else, it works. But you realize that, actually, I guess in this case, you don't really need it, but we're just making sure that we haven't already calculated the numbers already. So like if I called solve n, say solve 6 before, then I don't need, then the next time I need to solve for 6, I don't need to solve for it. I already have the values in there because it's not 0.
Why would that make A7 and B7 0?
So initially A sub n and B sub n are just initialized to 0. That's just the default value.
Oh, so you're checking it. So
Yeah.
You're only running it. Okay.
Yeah. Okay. Okay. Then let's keep going. Yeah, now we can finally explain why the Fibonacci sequences show up. If we look at this formula from before, B sub n is A sub n minus 1 plus B sub n minus 1. And we know A sub n minus 1 is equal to B sub n minus 2. Did that make sense? Okay, so if we plug it in, we see that that's the same recurrence formula for the Fibonacci sequence. So B sub n is precisely F sub n. And A sub n is equal to B sub n minus 1. So that's F sub n minus 1. That's where it all comes together. Okay, now let's talk about dynamic programming. We just talked about memoization and recursion, which is like a very basic concept that constitutes dynamic programming. And so what is dynamic programming? A technique for solving a problem by breaking it down into subproblems. So here by subproblems, I mean the same problem, except it's with smaller bounds. So in the case of Fibonacci sequence, the problem fib sub n is solved by solving the subproblems fib sub n minus 1 and fib sub n minus 2. We're solving the same problem. We're trying to find the nth term of the Fibonacci sequence. But here we're using smaller bounds, which is n minus 1 and n minus 2. And in the case of Riječi, which was the sample problem, to solve for a sub n and b sub n, we want to find the answers to a sub n minus 1 and b sub n minus 1. So we're reducing the bounds, but we're solving the same problem. And dynamic programming can be done recursively with memoization, as we just saw, or iteratively with like a for loop, like how we calculated Fibonacci sequence from bottom up. The recursive implementation is more intuitive. As we just saw, we just came up with the recurrence relation. We just turned it into code. So that was pretty simple, but iterative implementation is faster than recursive. And the key components of dynamic programming is initialization. So the base case, you know, your recursion has to end at some time. So it has to have a base case. And in the case of Fibonacci sequence, it's F sub 0 is 0, F sub 1 is 1. In the case of Riječi, A sub 0 is 1, B sub 0 is 0. And then there's transition. So this is like the difficult part of dynamic programming. You have to find the answer for a larger n, given the answers to the subproblems. So we know where dynamic programming is to solve a problem by breaking it down to subproblems. So if you have the answers of the subproblems, how do you find the answer to the original problem? So in the case of Fibonacci sequence, if you have f sub n minus 1 and f sub n minus 2, you can find the answer to f sub n, which is given by this formula, and the same thing for Riječi. So that's the basic idea of dynamic programming. Now let's do some exercises. In how many ways can you fill a 2 by n rectangle as shown with 2 by 1 dominoes? Here's a hint. Let S sub m be the number of ways to fill a 2 by m rectangle with 2 by 1 dominoes. So what you're trying to do is you want to find a base case and a transition. So what do you think the base case is? Yes? Okay, so the number of ways to build a 2 by 1 rectangle is to use one domino vertically, right? So that's saying S sub 1 is 1. That's a valid base case, but here we're going a step further and by saying S sub 0 is 1. You have one way to make a 2 by 0 rectangle, which is putting nothing down. So that's not 0 ways, because if it's 0 ways, then you're saying you can't make a 2 by 0 rectangle. But you technically can't. So we're just saying F sub 0 is 1. And how do you go from a smaller rectangle to a longer rectangle? Okay, so someone said to stack them. I guess normally we would think to stack them to the right. So let's see what happens if we stack some dominoes to the right. The rightmost dominoes have to be horizontal or vertical. Everyone agree? So let's see if they're horizontal. Then it must look like this, right? Then the number of ways to have the rightmost dominoes be horizontal is precisely S sub m minus 2. Because you just take a 2 by m minus 2 rectangle and slap 2 horizontal dominoes to the right. Does that make sense? Okay, so you're asked how many ways are there to fill a rectangle of a 2 by m rectangle so that the rightmost dominoes are horizontal. So if the rightmost dominoes are horizontal, they take up a 2 by 2 square, right? So you can fill the rest of the 2 by m minus 2 rectangle however you want, and then slap those on. So the number of ways is S sub m minus 2. And similarly, if the rightmost domino is vertical, then you can fill the rest of the 2 by m minus 1 rectangle however you want. So that's S sub m minus 1. Okay, so now we get our transition, which is S sub m is equal to S sub m minus 1 plus S sub m minus 2. Okay, so anyone have questions about that? Give me a thumbs up if you think you understand. Okay, cool. Now to something more complex. In how many ways can a robot move from the top left to the bottom right in an n by m grid when it only moves to the right or down at each step? And here's a hint for you. So let S sub I comma j be the number of ways the robot can move to some given position. So you want to come up with a base case, and then how do you move forward from that case? So anyone have any ideas for the base case? Yes? Could you repeat that? Okay, so there are two indices here. So you would say like S sub 0 comma 0 is 1, right? Okay, so here we're gonna use one base indices. So that would be S sub 1 comma 1 is 1. So there's exactly one way to get to the first square where you start, but you just don't move, right? And then how do you calculate for S sub I comma j given all the subproblem answers to the subproblems, like S sub I minus 1 comma j minus 1, stuff like that? Anyone have any ideas? So like, so how do you calculate for F sub I comma j given, I guess, other S values? Okay, maybe that's a little bit difficult to understand. You can get to the square where?
Or like this either down or right, say
Okay, I think you're close. Yes. Okay, can you explain your reasoning? Yeah, exactly. Okay, so let's look at this diagram, I guess. So to get to I comma j, the robot either moves down or right? So the robot either comes from I minus 1 comma j or I comma j minus 1. So if the robot comes from I minus 1 comma j, there's S sub I minus 1 comma j ways he could get there. And if the robot comes from I comma j minus 1, there were S sub I comma j minus 1 ways it could do that. So there's our transition. Now, does that make sense? Okay. Okay, now let's get to our second example, exact change. I'll give you a couple minutes again and have fun. So given this b sub m comma v, can anyone give me a base case? Okay, then I guess I'll reveal that the base case is b sub m comma 0 is 0. So for any number of bills, you can make $0 with the 0 bills, right? So how do we transition? So for the mth bill, we either use it or we don't use it. So suppose we already processed all of the m minus 1 bills from before. We're now looking at the mth bill. So suppose our mth bill is the $2 bill, and then we already had a $1 bill, a $3 bill, and a $4 bill. I guess those don't exist, but yeah. So if you look at the table, I've listed out the minimum number of bills we have to use for each of these values. And if you can't make it, then I just put not applicable. So using the first m minus 1 bills, I guess to make $5 is using a $1 bill and a $4 bill. And so we either use the mth bill or we don't. So if we don't use it, it's the same as using the first m minus 1 bills, right? And if we do use it, so we're forcing ourselves to use this bill, then we cannot make $0 or $1 because we're going to start with at least $2. So to get how many bill, what's the minimum number of bills we have to use to get to a value with the constraint that we have to use the $2 bill, we look at the minimum number of bills we use for v minus 2. If that doesn't make sense, I hope this does. So to make $2, we find that the minimum number of bills we need to use to make $0 is 0. Then 0 plus 1 is 1 bill. I feel like that didn't make sense, so let's just continue. So to make $3, we look at how many bills we had to use to get $1, and then we slap the $2 on. And since we could not make $2 before, we cannot slap $2 onto a combination to get $4. And the same thing continues, like so. So does this table make sense right now? Okay, so which part of it is not clear? Yes? Yeah, it's just 1, 3, and 4.
So you're saying you look at the m minus value bill that
It would be v minus, so the value minus 2. So you're trying to find the minimum number of bills So for, I guess, $10, you're trying to find the minimum number of bills you used to make $8. And then you add the $2 on. So that would be the minimum number of bills you use to make $10 with the $2 bill. Okay, so yes? Yeah. Why is, sorry, one? Oh, why is one and eight? Because in the I guess, third row in this table, we have to, like, we're forcing ourselves to use the $2 bill. We can't use the $2 bill and get $1 out of it. Did that clear it? So like the second row of this table is the minimum number of bills we use out of the first n-1 bills, which are the $1, $3, and the $4 bill. And the third row, we are forcing ourselves to use the $2 bill. Any other questions about this? If not, then give me a thumbs up. Okay, so let's continue. So since we either use the nth bill or we don't, if we don't, then it's the second row. If we do use it, it's the third row. Then we just take the minimum of them to get our b sub m comma v. So I guess for a value of $3, we can use the $2 bill to make it, but that would make us use 2 bills instead of 1. So we take the minimum. So we actually don't use the nth bill here. And I guess for $10, since we could not make it with the first n-1 bills, we have to take the $2 bill, and that gives us a minimum of 4. Now, does the last row of this table make sense? Just taking the minimum of the number of bills in the table or in the column. Okay, so now it's the same thing in words. If we use the nth bill with face value v, the minimum number of bills for a given value v is b sub n-1. So using the first n-1 bills to get a value of v minus f. And then we add 1 to that because we're using a new bill. Okay, now does that line make sense? Thumbs up? Okay. Any questions about this? So if we look at this table, the second row is, if we count the list in the second rows, it gives you the number b comma n-1 comma v, right? B sub n-1 comma v. Okay, maybe that was bad, but let me just try to explain this line again. So we looked at the first n-1 bills, correct? And we're trying to see how can we get to some value v with the nth bill who has a value of f. So since we're using a bill that has value f, we want to find the minimum number of bills we use to get a value of v minus f. And we want to find that value that's made up by bills in the first n-1 bills. So that's b comma b sub n-1 comma v minus f. Oh, right now we're just talking about the option where we force ourselves to use the nth bill. Yeah, so this is one part of it. Okay, now does that make sense? Okay, so now we'll talk about the other part. If we don't use the nth bill, then it's the same thing as using the first n-1 bills. So that's b sub n-1 comma v. So the transition would be to take the minimum of those. Okay, any questions about that so far? Or give me a thumbs up. Okay. So the answer, so now we have the minimum number of bills using all n bills to get any value v. So we will just have to find the minimum v that's greater or equal to p such that b sub n comma v exists. Note that like this can not exist because of these not applicable values. So like there are values you cannot make at all. Then we just don't count them. And here's the solution for that. Can you see my cursor? Okay. So here we read in a bill with value f. And for every value, we take b sub m comma v is the minimum between b sub m minus 1 comma v and b sub m minus 1 comma v minus f plus 1. Except we did something different in the code because we have to make sure v is greater or equal to f. And then at the very end, we start from v equals p, and then we find the first v such that we have some valid value, b sub m comma v. Does this solution make sense? If not, just hit me with questions. Pardon? Sorry, I couldn't hear you. Oh, INF. So we're trying to find minimums, right? So b sub m comma v are supposed to minimums. So if we put like a default infinity in it, then it's not gonna interfere with our calculations. Yeah. So if it's a valid value, then it's gonna be less than infinity. Yeah, here I just set INF to 105 because no answer can be greater or equal to 100. So 105 is a safe value to put there as a placeholder. Okay. Any more questions about this? Or give me a thumbs up. You have any questions? Did you understand this formula? The formula I'm showing right now. This transition. Okay. Okay, if you have any questions later, you could ask me. Yeah. Okay, now I guess let's go on to the third problem, compositions. This one, I'm honestly not sure if this one is easier or harder than the last one, but just think about a base case and a larger case. Okay, what about this? Let S sub n be the number of compositions of n. I guess that doesn't really help, does it? But like given that, can you give me a base case? Yes. Yeah, it would be 1. I guess it's kind of hard to think about it, but yeah, there's exactly one way to make it 0, which is have nothing in your expression. Sorry, what's that? Yeah, basically you're saying like an empty set is an object itself. So let's think about compositions of n that's greater than 0. So since it's greater than 0, then it must end with something plus x, right? Unless it's the number itself. So like if you have 5, then its composition must end in something plus something, like 1 plus 2 plus 2, 3 plus 2, 4 plus 1. I guess 5. It's not really plus something, but it's technically like a 0 plus 5. So if we think about it this way, and we have all the compositions of say 0 through 3, and we're trying to find the compositions of 4, we can add 4 to everything in the compositions of 0. We can slap plus 3 at the end of everything in the compositions of 1, and plus 2 to everything in 2, and plus 1 to everything in 3. Does that diagram make sense? Okay, so if we slap on a plus x to the end of something, then there are s sub n minus x such somethings we can slap it at the end of. Was that clear? Yeah. Okay. Then our transition is pretty simple. S sub n is s sub 0 plus s sub 1 plus dot 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 plus s sub n minus 1. Okay, that was not too bad. Now consider the original problem where we can't use any number of the form m plus I times k. So again, let S sub n be the number of compositions, but now under the constraint. What's the base case? Trick question, it's the same thing because you're using nothing, so you're not breaking the rule. And to transition, we follow the same logic, except here we slap a plus x to the end of some other expression, right? Now we're just, oops. Now we're just constraining it such that the x we slap on cannot be in the form of m plus I times k. And by induction, you're slapping on this plus x to every expression that doesn't violate the rule already. So you're still not violating the rule. So for example, if m and 2 are both k, that means we cannot use even numbers. Then these on the left are the valid compositions of 0 through 3. Notice that we did not use any even numbers, but we cannot slap on a plus 4 to everything in 0 because 4 is even. We cannot add plus 2 to everything in 2 because 2 is even. So we can only take from 1 and 3. Now, does that diagram make sense? Okay, then there's the code that's recursive. Let's see. So if we have already memoized this call, then we return the previously calculated value. If it's 0, then we turn the base case 1. And then if n is not 0, then here j is the x we were talking about. And here this if statement checks if x is not a part of the arithmetic sequence. So if it's not a part of the arithmetic sequence, we add solve parentheses and minus j to it. Does this code make sense? And yeah, that's literally it. That's literally the solution for this problem. And here's the iterative solution, which is just calculating the same thing bottom up. So we did s sub 0 is 1 first, and then for each larger n, we just calculate the same thing. Yeah, so dynamic programming, I guess, is just mastering how to do the base cases and the transitions. Yep, and that's it. And give us feedback. We do read them actually. And there's the contest. Thank you.